takeaways for this talk. So the first one is that, getting full and spiral merger breakdown waveforms in beyond GR theories is quite hard. But I'll tell you a bit about the progress in the last few years in this field, and then I'll also kind of try and convey to you that even though we might not have reached the accuracy that full and spiral merger breakdowns have in GR, you can already learn a lot from it, and I'll give you one cool example of where General Relativity, which is what we need to get those mergers, can maybe give some insight to people doing data analysis. But first, let me give you some context for what I'm going to talk about. So why do we want to go beyond GR? So forget about theoretical and observational reasons, even though there are many. We're also in a very exciting era in terms of the observational data we're gathering, and the data I'm referring to is gravitational wave observations, which kind of allowed us to test GR in a regime that we haven't been able to do before. And the regime I'm talking about is the one where gravity is not only strong but also highly dynamical. And so here you can see it's this kind of cute way of showing the events we have seen by the end of LIGO, Virgo, Kappa, terms observing them. So I think this is roughly 200 if I remember correctly. And now we're going to go to the fourth observing one. So say that we all agree that we want to test GR with gravitational waves. What do we do? So in all branches of physics, there's two ways we can test GR. The first one, which I think is probably the more intuitive one, is that you do the so-called top-down approach. So you modify your theory of gravity, theory of Einstein at the fundamental level, so we get the level of the action. And then you try and you derive the equations of motion, as usual, and then you want to solve the two-body problem. And here I want to emphasize that this typically requires a combination of various kinds of methods. So during the spiral, where the black holes are quite far from each other, people usually use post-Newtonian theory, so analytical methods. Then you have the merger, where here we require general relativity, and so this is what I'll be focusing on today. The reason people were quite excited about the merger in beyond GR theory is that people thought that maybe that's where you expect the eccentric, the deviations from GR to be the largest, because gravity is so nonlinear and strong there. And then you have the breakdown, where you have your black hole just settling to its final environment, and there we can use perturbation theory. Please interrupt me at any time if anything is okay. But say we solve the two-body problem, then what we can do is we can extract gravitational waves, and then we can go on and compare it to the data. And so here you have an example which, for those who followed the workshop last week, you might have seen this. So this was our very first gravitational wave event, 914. And what people did there, because they didn't have beyond GR waveforms, what they did instead is they compared the data to the GR waveforms we had, and you can see there's very close agreement between the two. But say we had a beyond GR waveform, we can go on and take the data and then compare it to whatever waveform we have and try and constrain our theory. This is presumably the way we could place the tightest constraint on whatever beyond GR theory we think is out there.
Yeah, no, but it's something that has to be said. You don't know a priori the astrophysical parameter. So by changing the astrophysical parameter, there's not one GR prediction.
It's a multi-dimensional problem.
And so, how can you pinpoint to a GR deviation once that cannot be reproduced by any of the astrophysical parameters? That's not it does.
Yeah, ideally you would have a template bank for one particular beyond GR theory, and then you would do this for every beyond GR theory. Like you said, it's a daunting task. And I think that's why, it's one of the reasons why people have not been using this way to test GR, and I'll be talking about this. So this is not what the community has been doing in terms of testing GR, and there's two reasons. So the first one is kind of what Ricardo is alluding to. Once you start thinking about what wants to extend GR, you can see there's many possibilities, and some people will favor some extensions over the other, but I don't think anyone has a very preferred theory, or I don't think there's a consensus on which theory is favored over the other, at least from a theoretical point of view. So then the question is, well, which one do you pick? But then the other one, which is more of a practical restriction for people doing numerical simulations like me, is that most beyond GR theories are going to modify the Einstein's equations in a way that you can't really predict what signal is going to look like during the merger, and that's a problem. So people have been doing a lot of progress in terms of the inspiral, the ring down, but the merger was quite tough until very recently, and so that's what I want to talk about today. So what the community has been doing instead is they've been using the bottom-up approach. So they've been, yeah.
Sorry, could you go to the previous slide, please? So you told us that the waveform is known beyond GR, those places.
Some, not all theories, but some, like for instance, scalar tensor theories, quantized theories, Einstein ether. A lot of people have been using post-Newtonian theory to at least derive what the signal is.
Is it possible to do some match, or does it beyond GR?
Yeah, so usually, well, you always, I mean, so far, you always need the merger for the numerical simulations for the merger. So you have things like the effective one-body formalism, where they use it's like post-Newtonian theory for the spiral, they use perturbation theory for the ring down, and then they use calibration to numerical simulations for the merger. But for that, you need a lot of, well, at least a few numerical simulations.
Is there any success in the sense that they found that non-GR theory fits reasonably well the data?
Well, I'll show you some results, and you'll see that the waveforms we have at the moment for beyond GR theories are actually quite close to the ones you would have in GR. But so going back to the bottom-up approach, what people have been doing there is just modify the theory at the phenomenological level. So here, for instance, you have an example where someone took a waveform in GR, and then you can, like, say, modify the frequency evolution or the amplitude or time to merger. But I should say this is completely theory agnostic. So, you know, it might be motivated from some theoretical another theory beyond GR, but, you know, this is just like a parameter detune. And this is exactly what the LIGO-Virgo-Carver collaboration has been doing to constrain beyond GR theory. So when you look at, you know, the LVK papers, and, you know, especially the testing GR ones, what you'll see is they do a bunch of, like, tests, and some of them are the so-called parameterized tests of GR. And this is like the results of one of those, where what they do here is they, going back to those post-Newtonian coefficients, they just modify each one of them at a time, allow for modifications, and then use the data to constrain those modifications. And then that's really as far as it goes for testing GR. So, you know, like I said, this is really suboptimal because you're not really constraining any specific theory. The one thing I should say is that supposedly, I mean, this can be mapped to a very large class of beyond GR theories, and I think that's the motivation for those tests. But I do want to emphasize that, you know, ideally, you still want to have a couple of waveforms and a couple of beyond GR theories so that you can at least test those tests and see how well they're doing, and maybe also motivate retests. And then, of course, if at some point we do end up seeing something, then we'll have to, like, you know, definitely get, like, specific waveforms. And that's where we'll have to do what Rico said, like the whole, like, shebang of having a template potentially and try and understand what we're seeing. But okay, so let me now I want to tell you a bit more about the progress in terms of getting the merger signal in beyond GR theories. So the community has been coming up with like 3 different approaches. So the first one is that you just restrict yourself to theories that possess a well-posed initial value formulation. And I don't want to get into the technical details of this, but this is just saying that we can like predict what the signal looks like. So we can solve the equations, like the Einstein's equations plus modifications on a computer, and we trust the solutions we get. So of course, you know, GR is one class of those theories that has a well-posed initial value formulation, but there's other theories that also possess a well-posed initial value formulation, such as, for instance, scalar tensor theories, but also quadratic gravity. You also have theories that only modify the scalar, they add an additional scalar part to the equations of motion, and they only modify that part of the equation. So those ones you can also use all the machinery we've been developing for GR. So for instance, the screening theories you might have heard of, or part of this class. And then you have another class, which is the so-called Harvesty theories, which are very popular in GR and those in cosmology. And this was also shown to possess a low-cost initial value formulation a couple of years ago.
What is CCZ4?
This is one of those formulations you can use to solve for the Einstein's equations on a computer. So there is the most commonly used ones are the BSSN, you might have heard of. It's just a way of writing the Einstein's equations that allow us to start with some initial data and then evolve forward in time. And the General Relativity formulation is one, the CCZ4 is one, BSSN is another one. So for instance, Pretorius, when he did his breakthrough in 2005 and got the binary black hole mergers in GR, he used the General Relativity formulation. A couple of months later, there was the Campanelli and Gusto group. They used the BSSN formulation to get the binary black hole in GR. And then CCZ4 is a slightly different formulation. Okay, but this is nice, but there's probably a lot, like, remember this diagram I showed you with all the theories, there's probably a lot of other theories you might want to look at, and that do not possess this like nice way of like casting the equations. So instead what people have been thought about doing is to use a order by order approach. So what this is really just solving the equations perturbatively. And this is just motivated by the fact that we think that the deviations from GR are going to be small anyway, so why don't we just introduce a small coupling parameter and perform an expansion of the metric and then solve our equations order by order. So what you can do here is you start at 0th order, so at 0th order you just have GR. Then you use this 0th order solution to like source the 1st order solution, which is usually when you have an extra degree of freedom, like in dynamic culture environments, that will just source the scalar field. And then you can like kind of keep going. And so what you would then get at 2nd order would be the leading order corrections to your metric. So this is nice because it's very simple to implement. It applies to a bunch of theories, but the problem is that it's prone to secular effects. And so, this has been used by a bunch of people. So Marshall Kupova and Stein, it has been applied to Einstein, Dilaton, Bosbonet, and dynamic culture environments. But yeah, it has some problems.
Sorry, what are the secular effects?
It's just that because you solve your equations order by order perturbatively, you're gonna get a secular growth there's going to be a secular dephasing between your true solution and your perturbative solution, which is going to accumulate. It's a bit like, when you're solving the simple harmonic oscillator, which has like a cubic correction, and you solve this order by order, you also get this, like you have this secular term that grows with time. It's exactly the same here. And so people usually either add more terms or use methods like the normalization group to like deal with that, but people haven't done this for the case of the binary black hole. The third method is the so-called fixing the equation approach. So this is kind of inspired by relativistic viscous hydrodynamics and kind of follows this EFT approach that our theory or modified theories of gravity should only be valid to some length scale anyways. So why don't we just modify the equations below that length scale, because we know they're not going to be valid. And the way we do this is the details are not too important, but usually we just add new fields and give those fields evolution equations. And I'm not going to talk about this method too much, but I wanted to mention it because it's like a method that a lot of people have been using in the community to get the merger in a couple of beyond GR theories, such as higher derivative theories and Einstein's double Gaussian invariants. And this method was kickstarted by Juan Cachuto and Luis Lenner. Yeah.
No, I'm intrigued by the last statement because I was thinking that you were about to talk about all the modifications we were talking about are UV modification. But then in the last statement you want to affect the IR.
No, so this is so fixing the equation is, in principle it works nicely, but the problem is that you have to add an additional time scale to drive those auxiliary fields. And this additional time scale you have to introduce is kind of ad hoc. So you want it to be small, but it can really be anything. And so for that reason, more recently, Paul Figueres, Aaron Held, and Aaron Kovacs came up with a more natural way to like introduce this ad hoc timescale. But what I'm saying here is that it's not very clear at the moment whether the way they're fixing the equations affects the DIR, which obviously you don't want. So all that I was saying here is that it's people working on this, but it's still I guess unclear whether this method is going to work.
So, are they still fixing the equations, or is it like do they still introduce new degrees of freedom and actually?
Yes. Yeah, they are.
Oh, they are.
Okay, and so you can, the question is really like, because I just showed you there was like 3 methods, right? There was one which is you just solve the full equations. That was the first method, so you don't really approximate anything. But then you're only restricted to the theories that possess a robust initial value formulation, and that's why I then introduced those 2 approximate methods. And so you can always ask the question, well, how well are those approximate methods doing? And we can talk about this more if you're interested. So we looked at this in a paper with Louise and Guillaume Diderot last year, but I didn't want to talk about it right now because I thought it was a bit too technical. So what I want to do instead is I want to focus on one particular theory and use the first method and then show you what kind of deviations we expect in this particular theory. So the theory I'm going to look at is Einstein-scalar Gauss-Bonnet gravity. So for those who haven't heard about it, the way you get to Einstein-scalar Gauss-Bonnet gravity is just by introducing one extra degree of freedom, so phi, and you couple it to gravity through the Gauss-Bonnet invariant, which is this combination of Riemann here. You're still free to choose the coupling beta, which we in the first part of the talk are going to consider to be just proportional to the scalar degree of freedom. So we have this coupling constant lambda here, which is just going to tell you how large the modifications to GR are. So why this theory over another? I mean, remember this very large diagram. There's 2 reasons. The first one is that we can solve the full equations of motion, so we can actually be sure that we trust the solutions we're getting. So that's the first reason. And the second reason is that this theory is actually quite interesting from a phenomenological point of view, in the sense that it's consistent with gravitational wave observations in the, well, it's just consistent with observations in the weak field regime, but it's expected to give deviations to the strong field regime. And the reason for that is that black hole solutions, for instance, Schwarzschild are not a solution to the equation of motion. Instead, what you have is that the black holes are always going to be surrounded by some scalar pair, which is going to be inversely proportional to the mass squared. So what you have to imagine is that you just have a black hole with some kind of scalar, massless scalar plot surrounding it. So this is not, the process that Niels was describing the other day. This is not super rigorous. We have a massless scalar plot here. And the reason why this is interesting is not what you have is because you have this scalar plot, you're going to have an additional energy channel through which your black holes are going to lose energy when they're in a binary. And for those who are familiar with post-Newtonian theory, this is going to notify the signal at -1 km. So at low frequencies.
So you said that if lambda equals 0,
Then you just have GR.
but you have GR plus the scalar which is coupled to GR already.
Right, because it's just a pretend, like you just have this term, right?
Yes.
So that's not going to modify the dynamics.
No.
No.
Is that really thing to see?
I think if you derive the equations of motions, it should be trivial to see.
Like the scalar field, the trivial solution, or like a minor black hole solution, will not source any scalar field.
I guess you'll just have box phi equals 0. And so it will always think here.
Why is it, you have a coupling now between phi and the gravity sector.
But he was asking if lambda is 0.
Okay.
Yeah. Okay, and so now what I want to do is I want to consider both binary black holes and black hole neutron stars in this theory, and just to guide the questions I'm going to try and answer is, well, what does the gravitational wave signal look like in the nonlinear regime? Because that's kind of why you need General Relativity for. So are there any new signatures or important nonlinear effects? I mean, this is a big question people had before they were able to simulate those things. Like, is there anything crazy happening in the merger, which would be really important to like rule out those theories? And then what about the breakdown? Just because there's been a lot of attention on the breakdown in the community, and so we wanted to see, well, is there again any kind of interesting signature? So let me show you a movie first. So this is an equal mass, I think, yeah, equal mass dynamic black hole. This is the scalar field, so you can see it's like larger closer to the black hole and then kind of falls off. In fact, it has like a 1 over r fall off. So it's r. And then they merge, and then you can see well, I hope you saw that the final black hole, the kind of the color was not as bright, and it's because the remnant black hole is larger, and so its scalar charge is smaller. Because remember, it goes as 1 over the mass squared. But okay, let's have a look at the gravitational wave signal. So on the left you have the gravitational wave signal, on the right you have the scalar radiation. So there's no equivalent of this in GR. So the solid purple line, this is GR, and then those are like different components. The values are not so important, the larger the modification to GR. So I think the important, so here they're aligned at the merger. And the main thing to see here is that you can see this, all those signals look very similar. So in fact, if you look at the zooming here.
So that's with the same astrophysical parameter, or would be
yeah.
the same?
Same as, well, same initial. Yeah.
Same initial data and the mass is in, so I guess it's mean equal to 0.
Yeah, so this is an equal mass non-spinning dynamic black hole. Regarding the masses, it's a bit tricky because solving the initial, like constructing initial data for those black holes and those beyond GR theories is also a complicated problem in itself. And so what we did here instead is we started with 2 black holes in GR, and then we sourced the scalar field as we go forward in time. What that means for the masses of our black holes is that as the black hole scalar rise, their masses are going to reduce because some of the mass is going into the scalar field. So the ADM mass of the spacetime is the same, but the individual masses of black holes is smaller for the cases that have a scalar field.
The scalar field does it follow around the black hole? I mean, what's the profile?
It's like a 1 over r profile. So it kind of like starts on the horizon and then it kind of decays. And it's like 0 at infinity, but that's like construction. That's like a boundary condition.
Okay, but now, this 1 over was the typical thickness of this ghost owl. What I mean is that if the ghost owl goes exceeds the size of the binary, then you have an actual.
Well, you can see here, right? I mean, it kind of like very quickly.
It doesn't exceed.
So yeah, I mean, I guess there's like a physical going along here. I mean, they started at whatever 10 hour apart. But yeah, so I think that the main takeaway here is that there's a very weak dependence of the amplitude on the coupling. So even though you increase the coupling, you can see the amplitude doesn't increase that much, which is something I guess we didn't really know before doing the simulations. So people might be thinking, okay, well that's a bummer. How are we gonna even constrain this theory now? But remember, I told you that we still expect a modification, like leading order at -1 p.m. And
those are still little values for lambda, aren't they?
They're what?
Little values, small values.
Well, they're not that small. I mean, the 0.1 is actually roughly the order that we, like, the tightest bond we have on this theory is roughly of the order of this. So we've already constrained this theory to be around this value or for smaller. And in fact, there is no black hole solution that can support a scalar error for a value of lambda above 0.23 in those units.
And what happens when you reach the value or?
You can't form the black hole horizon is no longer regular. So you just can't solve the equations of motion for like a single stationary black hole.
And if you're a little above this value and you do a simulation,
it will crash. So what you have is you have your equations become elliptic outside of your black hole horizon. Yeah. We've tried this. Like you increase the coupling and then at some point it just, yeah. And people have looked at this in detail. I can refer you to something with it here. But the interesting signature for this theory is that, remember I told you had this, like, you expect this -1 p.m. modification. And what this really means is that, not because we have this extra channel through which the black holes are losing energy, is that you expect the beyond GR waveforms to merge faster compared to GR. And so this is again the gravitational wave signal for different mass ratios. So here you have equal mass 3 to 2 and 2 to 1. But let's just focus on the top one here. So again, you have like GR and different couplings, and what you can see here is that the dotted one merges a lot faster than the GR one. And so this is really the main signature for this. And I think this is interesting because it means that, you know, I mean, we still have to do this, but potentially this means that maybe we have seen this, you know, a signal like this. It's just that it is probably degenerate with some other GR parameters, and you know, it's not impossible that if you were to give inject a signal like this and then try and recover it with a GR template bank, you would still get a good fit.
Well, you try. I mean,
yeah, this is something I'm working on. It's just like getting those, you know, it's one thing to implement solutions you trust, but then it's another thing having them to the precision and the eccentricity required for like doing those injections in like
So qualitatively, can you understand qualitatively the reason of this huge shift?
It's just you have an extra scale, you have a non-scalar channel, you have an extra channel for which your binary is losing energy.
Yeah, but
and it's proportional.
They should speed up. The merge happens earlier. That's it. The merge happens
earlier. Yeah, exactly. So to lead in order the charge, so the amount of scalar radiation being emitted is proportional to the difference between the scalar charges of your binary. So which means that if you have an asymmetric binary or a black hole neutron star, so that's what I will talk about just now, where only one of the constituents has a scalar charge, then you expect more dephasing.
So I think I missed the point. Your argument is that still, I think there's a lot more happening there if you have this theory working on, I mean, your blue plots, dots.
It really, I think maybe this is just the rendering of the plot, and because it's like cut off to like just focus on I think we wanted to focus on this part, but really it mostly just shifted. It looks very similar. In fact, you can see this here, like where we just aligned the like merger, you can see that it looks quite similar.
This color has to be massless, no? If he has to take out energy.
It's massless.
Yeah, aren't there other bounds on the coupling of a massless scalar to matter?
On this theory, no, there's, I mean, at least
But
for the
here you must have a free parameter, not the coupling of the scalar to your source. And this in general is heavily constrained because we don't see any.
It's constrained in the weak field regime from like whatever solar observation stuff like that, but it's not constrained for like those next scales where you know, I guess here our black hole is like kilometer scale, right? So our lambda is also around kilometer.
Yeah, but okay, the field Gauss-Bonnet does this. Does something that doesn't couple a long scale but couples a short scale because of the derivative in the Gauss-Bonnet.
Yeah,
that's what. Okay.
Yeah, exactly. We want Riemann to be extremely high.
Okay. I mean, that's okay. I see. So
okay, so this was binary black holes, but we also decided to look at black hole neutron stars, and the reason for this was because of what I just said here. So it turns out that in this theory, neutron stars do not have a scalar charge. So this is kind of the opposite of like scalar tensor theories. So in scalar tensor theories, neutron stars are scalarized, but black holes are not. And that's also why scalar tensor theories are actually so heavily constrained by pulsar observations. But Einstein's scalar cosmologic gravity just evades any of those constraints because neutron stars do not have a scalar charge. But the other thing is that because now the neutron star does not have a scalar charge, you expect quite a large dephasing during the spiral. Now, of course, this is only useful if we're actually seeing those systems. And so another motivation for this work was the two events we saw around, I think one of them was in 2021 with the LIGO-Ribo-Cagra kind of collaboration. And turns out that it's actually those events that allow us to like place the strongest constraint on Einstein's scalar cosmologic gravity. And the reason for this is because those events have a very long spiral, and because ESGB modifies the gravitational wave signal at -1 pm, it's at like low frequencies that you can actually place really strong constraints on this theory. So what we decided to do with Bill is to take the parameters of those two events and see what they would look like if we had Einstein's scalar cosmologic gravity.
Sorry, what theory of gravity is that?
It's still the same.
What?
We're still looking at the same theory.
Einstein, what else?
Scalar cosmologic. Yeah. So let me first show you a movie. So one thing I want to emphasize here is, so the blue dot is the neutron star, is that even though it doesn't have a scalar charge, it still has some scalar profile. It's just that it falls off very quickly, and that's why we say that it doesn't have a scalar charge. And then it gets absorbed by the black hole. Okay, so this is the signal. So here in the solid line, we have GR. The dashed line is one particular coupling. Again, it's not too important the value. And this is for a black hole of 5.7 solar mass and a neutron star of 1.5. So here the neutron star was not tidally disrupted before the merger. And so you can see here again, like for the black holes, there are very little enhancement at merger. You can just see this like dephasing. So same story. And yeah, you can see this here again. So here this is again the gravitational wave signal, but now looking at a range of couplings, and on the right side we now have a 3.5 solar mass black hole or 1.5 solar mass neutron star. So this was for the second gravitational wave event we saw, and here we actually picked an equation of state such that the neutron star is tightly disrupted, because we thought maybe this would give some interesting signature, but as you can see, there's not much happening. I also said I would talk about the breakdown, because talking people have been looking at it quite heavily in the testing GR probability. So what most people have been doing is computing how the frequency of the signal changes for the quasi-normal modes. But instead, what we found actually is that the shift in frequency is very small. One point out very interesting to look at. What we find instead is that you can have like either a reduction or amplification in the amplitude of the breakdown signal, which is what this is showing. So this is the amplitude of the gravitational wave signal as a function of time after the peak. And so by showing this, what we're trying to do is maybe try and tell the gravitational wave community that they should come up with like tests of GR where they modify the amplitude of the gravitational wave signal instead of like focusing on the quasi-normal frequencies. Any questions about that? Okay, so this is I want to complete the first part of my talk. So I really want to emphasize that this is a big deal. People have been working on this for quite a while. It's kind of really hard to get the merger and beyond GR theories, and that's why progress has been so slow. But progress the last few years has been quite good, and we're finally able to maybe do injections and we can potentially do injections and like I was telling Ricardo, try and look at degeneracy and things like that. We can also try and maybe test and improve some of the theory agnostic tests people in the collaboration have been coming up with. And of course, I showed one example theory, but in principle, the tools we developed can be applied to any theory within this larger class of Hornetsky theory of gravities, which typically have a large number of applications in cosmology.
In the moment, you still don't have the complete waveform?
No, we do. So now we have inspiral merger right now. Yeah. But only for a few systems. Like those simulations are expensive. So yeah, we definitely don't, and we don't want to make a template back because that would require simulations. Any questions about that?
Do you have some intuition of what the difference in GR would be for other kind of systems without having to do all this numerical work? If they would have a shift as well? Or?
Yeah, so people have looked at, if you were to include a master or something like that, it would affect the dephasing a bit, maybe the amplitude, but I don't think anything crazy different would happen. I'm not sure about if you were to go to higher order. That I don't know. Yeah, and in fact, I don't think. Yeah, no one has looked at this even just from a PM perspective. So we don't really know in the well either what would happen. People have focused mostly on Einstein's scalar gravity, which is quite a shame, but at least it has allowed us to compare between different methods and so forth.
So let me see if I understood correctly. This ion theory, GR theory, has chances to be applicable to waveforms. In those situations, neutron star and black hole, or any black hole?
Black hole as well, neutron and neutron star.
And why did you pay some attention at the end of your first part to the black hole, to the neutron star?
So we studied baryon black holes first because that's what we've been seeing the most with our detectors, so it seems reasonable, and also because black holes are scalarized in this theory and neutron stars are not. And then we looked at black hole neutron stars because those are the ones that give us the strongest constraints on this theory, so it seemed like a good idea as well. And in fact, I have not been involved, but Will East and Franz Pretorius looked at binary neutron stars as well. But there's nothing really interesting happening because, like I said, the neutron stars do not have a scalar charge. So if you put two neutron stars together, you're just going to have GR during the spiral. And then I think the question they were trying to address was whether anything interesting would happen in the merger where you form a black hole. But they found that this was happening at frequencies too large for detectors to see. So now I want to spend my remaining time on trying to motivate, why we need those simulations to maybe try and come up with new tests of gravity, agnostic ones. And so this is work in private with a couple of people at the Max Planck Institute, and also in Caltech. So the starting point is going to be the same. So we're going to be working still within Einstein's scalar gravity, but now we're going to pick a slightly different flavor in the sense that our coupling beta is going to be slightly different. So now we're going to be no longer proportional to the scalar field, but we're going to have a quadratic and a quartic term. So now our equations of motions are going to be invariant under parity flip, so under phi goes to minus phi. While in the past, our equations of motions were invariant under a shift in the scalar field. So why are we doing this? Because you can show, if you derive the equations of motions, that now GR is a solution to the equations of motions. So what you can have is, if you look at this figure here, so this is the scalar field on the apparent horizon as a function of coupling. What we find is that for a small coupling, what you just have is a GR black hole. But as you increase the coupling, at some point your black hole is going to scalarize and develop this scalar field. So what this means in terms of like binary black holes is that we now have like different options. We can either have two non-scalarized black holes, we can have two black holes of similar charges, or we can also have two oppositely charged black holes. And this is just because our equations of motions are invariant under this flip of sign.
But yeah, now can you comment a bit more on how you can get opposite charges? So you give a seed into the other direction, or just some random fluctuation in the beginning?
Exactly. Yeah. So I mean, this is still, the formation channel is still questionable. We don't know, and people haven't really looked at this. I mean, I guess one thing I should say is that if you had some kind of cosmological background, scalar field, then they would have, all the black holes would have the same sign in the universe. So here the idea, so actually I want to focus on this here, and the idea here is that, I mean, of course, you always want to look at this as a benchmark theory of phenomenological approach. I'm not saying this is a true theory of nature, I'm just trying to use this as a concrete example of what might happen. But yeah, I mean, the idea is you would just have a random seed that perturbs one black hole in one direction and the other, and the other. Say when it goes supernova and the black hole is formed, then it might just go either. But so yeah, in this talk we want to focus on that scenario. So you start with two oppositely charged black hole. So what we're going to do is we're going to use a combination of different methods to try and see what happens when those black holes are. So the first thing we're going to do is we're going to just solve for the initial data. So what I mean by this is just the black holes are kind of standing still, that relatively large separation, and we're solving for the Einstein constraint equations at that particular separation and instant in time. And the reason we're doing this is because it's cheaper than doing the full evolution. We can learn quite a bit from it. So what we did is we solved for this the initial data, both in like the separation space and also the coupling. So at different couplings, at different separations. And what we find, so we did this both for the similar charges and the opposite charges. So if you do this for the similar charges, what we find is, so here again we have our coupling on the x-axis, scalar field on the y-axis. This line here is the threshold for an isolated black hole to spontaneously scalarize. And so what you can see here is that you have a shift in the existence threshold when you have two black holes that are that have the same sign. And this is not something I will focus on, but I do want to mention that this effect is the one that typically gives rise to dynamical scalarization, which is kind of, I don't know, yeah. This is a phenomenon where you have two black holes that are initially just GR, and as they get closer, at some point, their interaction is going to be such that they will both scalarize, and this will affect the orbit. And this is something that was studied very early on in scalar tensor theories, but with neutron stars. So this is a well-studied phenomenon. But what we want to look at instead is the case where the black holes are oppositely charged. And so here what we find doing those initial data sequences is that the shift happens in the opposite direction. And so the question is, well, do you get something like the inverse of dynamical scalarization? And what this would mean is that you would start with two oppositely charged black holes, but then at some point, when they get closer than a certain length scale, then they would lose their scalar pair, and then you would just recover GR, which is what this picture seems to indicate. So what we're going to do now is we're going to perform evolutions. So we now have a brief idea of what might happen. So we want to run evolution and see whether we see anything interesting.
So, sorry, what do you mean? The value of field A, which, what does it mean?
It means apparent horizon. It's the value of the scalar field on the horizon of the black hole. So these simulations were performed with the Spectre code, which is the code developed by the SXS collaboration, mostly with Caltech, but also Cornell and Max Lab. So this is going to be this is an open source code. And I don't want to get too much into the details, but this code at the moment can only get the scalar evolution. So there's no back reaction of the scalar field on the metric. But nonetheless, what they found is that you can, if you start with two oppositely charged black holes and you can move them forward in time, what they found was exactly what I was describing, is that at some point one of the black holes will lose its scalar charge and it will acquire the same scalar charge as the other black hole, which is what you can see here, like those lines that kind of recombine. So you might be asking, well, why do they not? So I should say this is for equal mass binaries. So you might be wondering why they don't go to 0, as you would expect from the initial data sequences. And this is just because this is like for numerical reasons. So black holes, when we do numerical simulations, are not exactly equal in mass, and so this is why one of the black holes acquires the scalar charge of the other.
So this is the plot of.
This is
scalar charge.
the scalar field on the apparent horizon as a function of time.
The evolution of the scalar.
Yeah, and that's so here you can see the orbit. So you can see that at first. Well, it's hard to see I think here, but there's like two colors because there's a positively and negatively charged black hole. But then past a certain separation, which is this cross here, then you can see there's only one color because not both black holes have the same charge.
So, sorry, in this description, they become a unique black hole. It's because of the scalar radiation only.
It's because of the curvature of the two black holes as they get close enough will at some point start affecting each other. And that's where one of the black holes starts losing its scalar charge and becomes acquires the same scalar charge as the other. Maybe this is more clearly seen here. So these are simulations that we then did with a fully coupled code. So this is using the same code as the one I described in the first part of my talk. Where here we actually do have the back reaction of the scalar field on the metric. And so you can see this more clearly here that at first you have a black hole that has a negative charge, the other one has a positive charge, and then at some point it starts losing its scalar field, and then you have larger on the other. And then the final black hole is just GR. What's interesting, which you can see in the bottom panel here, is that, so this is the scalar radiation. So these are the spherical harmonic decompositions of the scalar radiation. And what you can see here is that at first the scalar radiation is dipolar to leading order, but then when when both black holes suddenly become line charged, then the scalar radiation becomes quadrupolar in nature. So you have this like change in the multipolar structure of your scalar field. But the real question is, how does this affect the gravitational radiation, which is kind of what we're seeing in the detectors, right? And so here you have the gravitational wave signal at the top, and at the bottom you have a measure of the eccentricity in the signal. And the reason we looked at eccentricity is because this is something that we look at in our gravitational wave signals we're seeing with our detectors. And because gravitational wave radiations just dissipates out any eccentricity, all the signals we've been seeing are quasi-circular. But what we're finding here is that there's again a dephasing between the GR and the beyond GR waveform. But on top of that, this dephasing is basically enhanced because of the introduction of eccentricity in the signal. So what's happening here is that you start with two black holes on a quasi-circular orbit, but then at some point when one of the black holes loses its scalar arm or scalar charge to get the same charge as the other black hole, it loses mass in the process, and this gives rise to eccentricity in the orbit. And this is interesting because this is something we could potentially maybe look for in our data, because we don't really know any other process that would lead to a sudden change in the eccentricity on such short time scales during the spiral.
So the time scales for this T-scalarization, what is this like that?
It's around it's less than 100 M, roughly 100 M.
But like the scalarization is like an exponential, is that equal to that version of that?
I guess you would have to read support this, which I don't know.
And throwing away the scalar charge will result in an increase of the mass of the final report, increase of radiation. Yeah.
So this chain gives rise to a reduction of the mass of both atoms.
No, for the remnant, I mean.
Oh,
Because the remnant basically has no charge, right?
yeah. So all the scalar radiation is being dissipated.
Okay. So that leads to some additional radiation, but scalar radiation.
Scalar radiation. So you would have to somehow introduce a coupling to the matter if you would want to see this.
No, but wait, the scalar radiation, is it charged under the scalar itself? I mean, it's like the photon, like the graviton is charged under the gravity, no? Because it carries mass. But the photon is not. It's not charged. So for the scalar, what would be the case? Scalar radiation, does it carry charge of phi or not?
No, I don't think so. Because it's massless.
Not charge of phi, not of gravity, charge of phi. Because if it doesn't carry charge of phi, I mean, who carries away the charge?
No, I mean the black hole does have a scalar charge.
Yes, no, but that's my point, no? There's a scalar charge at the beginning, it doesn't have at the end, no? That's what you're showing, no? The branch. So who carries away the scalar charge?
Oh, I see.
If the scalar,
I think it goes to infinity.
yeah, but that means that the scalar radiation is charged under the scalar, is it?
I guess. Yes.
So is the scalar charge actually preserved? Like, is it a charge in the Newton sense, or is it just a 1 over r fall?
Well, if it has radiation, no, then it must be conserved somehow, otherwise it wouldn't be radiation.
It's just that you start with 2 optically charged black holes, and then you switch to the same charge. So somehow, either you have a huge burst of scalar radiation at that point, or the
No, I
charge.
mean, there are two separate, okay, there are two separate issues. First, if the scalar charge is conserved. Second, if radiation of scalar charge carry scalar charge or not, sure. Okay, what I guess that since the scalar radiation is, the scalar charge, is diffuse in the scalar profile, I have no problem with meet the fruit of this scalar, provided the profile changes accordingly. So what I mean, there are two things. One is the charge carried by the profile, the 1 over r that was, and one is the scalar charge carried by the wave. So in gravity, they are easily distinguishable, like for the photon, because there are different polarizations. But scalar is one polarization. This is always something that always passes me. In gravity and in electromagnetism, you can distinguish one polarization longitudinal and the other is not. For the scalar field, you have only one polarization, obviously.
Yeah.
So how do you distinguish what is the longitudinal field and what is the radiation field?
Well, I think you would have to couple it to matter for that. You would have to introduce a coupling.
Yes, because usually what people do in the scalar gravity, so they say, okay, there is a contribution to the Newtonian potential, so there is an addition to the Newtonian potential that comes from the static 1 over part, and there is the fact that the scalar couples to the moving dipole. Since the dipole has an oscillating pattern, the phi produced by that will have an oscillating pattern anyway. But yeah, then yeah, probably the charge is not conserved. How do you see the conserved? You should look at the conserved energy momentum of the scalar, and you should check if it is conserved and so on. Probably it's not conserved.
Right, yeah.
It's only conserved in gravity.
Yeah.
So it's not conserved and so on.
Yeah.
Okay, this will be checked probably easily later. Sorry for the
No. Yeah. But yeah, so going to your question, I don't know about the default, but it's quick. But I guess I could complete that. But it's much shorter than the overload.
Yeah, I guess my question is, how does it scale with the remnant problem? Like, is there a quote remnant space in which it is longer than the golden time scale?
Right. I don't know. I guess this is also coupling dependent.
Right.
But yeah, so I think this is interesting. I mean, this is is something that could potentially, I mean, I know this is a very specific theory and this is a specific corner of the parameter space, but I think this is an interesting phenomena that realizing that beyond GR theories can have such effects on the signal. And so maybe one of the beyond GR tests one could think of is to cut our signals into different parts and then see whether there's eccentricity being introduced from one patch to the next one or something like that. So with this, I just wanted to conclude that I hope I convinced you that getting beyond GR waveforms examples, at least in a few beyond GR theories, can help us maybe give us valuable guidance to how to improve our multivariate theory agnostic tests.
What do you mean by theory agnostic?
So these are the kind of phenomenological tests that the collaboration has been doing to test gravity. So it's you don't consider a specific theory. You remain theory agnostic. So you introduce modifications to your waveform, but without considering one specific theory. So you can introduce some modification to the amplitude or the frequency of the signal, but you just use an ad hoc parameter for that.
But in that case, you don't know theory, it's just...
In that case, it's just theory independent. And then you get a constraint, and then you do with that constraint whatever you want, I guess. But it's kind of, without very specific predictions, it's kind of the best thing we can do. And so that's also why people have been doing this up till now. Yeah, that's it.
Thank you.
And yeah, I'm here for the rest of the week.
Yes, any other questions? Sorry, if I can see half an hour of your time, I would like the student to tell you what you're doing, so you practice in telling other people what you're doing. Okay. Yes. So let's start with it. No, sorry, but I don't want to cut the discussion short. First, if you have questions. Okay, my time. You want to summarize in 5 minutes your master project?
Yeah. So I basically started downloadables, it's in the beginning. But what we're doing is that we are looking at cubic corrections to GR and the effective field theory problem. So it doesn't affect the equations of motion. And yeah, what we want to do is we want to calculate different corrections to the potential and the relative sector, and see how these corrections compare the cubic corrections compared to tidal effects, because there is some indication that you can look at these cubic corrections as tidal effects, so as finite. Looking at your sources not as point light, but as they have some finite size, and yeah,
so I guess the idea would be that people have been thinking of, I guess you could use waveform models that include tidal effects to constrain the tidal parameters in your permutation wave signal, and then you could potentially map this to your.
Yeah, I think that would be the part where we connect with.
Yeah, they are going to be cubic, some cubic corrections are the not all cubic corrections, but some cubic corrections are the channel with the tidal. And by the way, do you have some? You didn't consider tides, or you don't care because you start everything into numerical solution. But you discard sharp into tides into the black holes.
So it's something Laura von Naab has been looking at. I mean, we didn't scale up tensor theories, but then there's a mapping you can do to actually scale a correspondent. But it's at quite high PM.
So it's not 5. 5 PM is the usual way tidal correction center in EGR. It's just that in EGR for that there is zero position, but in this is what
no, there are tidal effects in this theory as well. It's just that here in numerical simulations you get it.
Yeah. No, because there could be, if one could envisage a way to isolate tides, if you measure the tides which is different from zero, that is smoking kind of GR.
Right.
But I wouldn't know, a simple way to isolate effects.
Yeah, I know it's something that some of the people doing those parameterized tests are working on to like constrain the tidal coefficient from gravitational wave events.
Yeah, no, those parameterized tests, I mean, you just add the term to the spiral,
Okay.
and you fix what the other, and you vary, and you see when it gets results.
But yeah, I don't know how you would extract the tidal effects from the numerical simulations. I don't know if you can do this.
Yeah, principally you can, if you have sufficient computing power. I mean, it's 5 p.m., you just need to like resolve it.
Yeah, but how would you extract the 5 p.m. piece? I guess you would use a waveform model to subtract off your diffusing. Look at the phase evolution.
You can take two binaries in which the tidal effect is, and then you can check the diffusion.
Well, but you have to be sure that everything else is equal.
Yeah, exactly.
And how, well, that's the equal, and how do we do it? To change, to tune only one thing and leave the rest. So you must have some analytic understanding of what is the tides induced by.
Well, that's what people do for binary neutron star waveform models, right? They use binary black hole models and then they add the tidal effects. And then they compare it to numerical simulations and then they find a better agreement that one they don't have chance.
So these two, they are numerically or analytically?
So the waveform models are analytical, but then they kind of like confirm, they kind of calibrate that they use numerical simulations and compare the agreement. So they look at the overlap.
There are tidal AOD now available in the market. So you can use tidal AOD and tidal AOD with the tides equal to 0. That's something.
But it'd be very challenging.
But I think
highly effect.
right, but I think if if now they derive the tidal effects for some beyond GR theory, and then we can use theory. Maybe you don't need to have a numerical simulation. Right? You can use theory constant test.
So what? Now what we're doing, we're not really going to the test. Actually, now we want just to get the analytics at the end prediction.
But I think once you have that prediction, then
Did Rami looked at the high derivative, right?
yes.
And saw some defects. Did they quantify the
Yeah, but I think their simulations are not accurate enough.
Let me ask you a more simple basic doubt. When you do the simulations and you have two black holes nearby, how do you give the space and metric to the computer? What sort of metric do you give to it as a starting point?
So it's all numerical. So what we evolve is the metric, the time derivative of the metric.
And what's your initial metric where you start to do the computations?
Oh, so what we usually do is we superpose to GR black hole solutions, and then we solve for the Einstein equations of the initial time step, the constraints equations. And so we typically we start with a superposition of two black hole solutions, say two Schwarzschild, and then there are some corrections to make sure that the combination of both of those solutions satisfy the constraints equations, and then we evolve forward.
So you start with a sort of superposition.
Sort of, yeah. But yeah, and then we solve for the constraint equations on the initial time slice.
Anything you want to add? So where are we in the project now? You computed the variation in the potential?
Yeah, I did the potential and I studied the relative part.
Okay. That you don't have the result yet, you're doing.
No,
Okay.
And I guess you're not, has anyone looked at the conservative part?
Oh yeah, the conservative is the, the first thing.
Okay.
No, there are several results in literature already. And some of them are conflicting, that's why the project was initiated.
So are you going to use a different approach, or they use?
No, basically, okay, the bottom line is the following, is that when you have a cubic extra coupling, so this was Luis brought it to my attention first, no? So here the two massive particle, if you have an additional cubic coupling, if this is of the Riemann to the cube, or if it is of the Ricci Riemann square, this is qualitatively different. It's not quantitatively different. Because basically what happens is this is proportional to the equation of motion. So when the Ricci put it here, what happens is that this diagram becomes this. Because if you put something with this k square on the top of the propagator, it kills the propagator and becomes this. And this is the diagram of a tyrant effect. So this is why basically this effect is degenerated with the time. The problem is that you must have a prediction. So the problem is that the times here is an unknown coefficient. Like this term in the bulk is an unknown coefficient. So unless you really know the coefficient, you cannot do much. Or just take a parameterized prediction.
I see. So you're trying to get that prediction.
So yes, I'm an EFT person, so I do, everything looks like EFT. Like everything looking into a camera.
Sure.
So the tidal effect scale is the cutoff of
Scale? No, it's an unknown coefficient, so you can put whatever you want. The point is that those two coefficients are basically the same because of the reason I told you.
Yeah, they're related to
Okay.
But
But if you had like a binary black hole merger and you measured the tidal effect and you said the tidal effect are below some number, then you can place a constraint on the whatever C1 and C2.
yeah, not C1 because C1 2, that's qualitatively different, but the C2, basically the C2 is a filter defined time. Just filter defined, so it's unobservable the difference. It's a filter definition. So now you're studying the emission, and then the following thing, but then it might be harder to go basically in that theory of gravity and actually compute the tides. You know how people do this. Basically, they take they solve the Einstein equation for a spherical symmetry. If you're doing gravity, you take charge, of course, and then you add perturbation on the top of it. And in gravity, you check that there's no perturbation, there's no quadrupolar static perturbation on the top of space. You just cannot do it. Because if you allow perturbation, that causes one, the quadrupolar perturbation should go as 1 over R2 infinity, would blow up at the horizon. So if it is anyway finite at the horizon, it must be 0. So that's one way to demonstrate there are no tides in GR. But as soon as you move out of GR, you get some tidal deformation at the horizon. And for that, you just have to solve the Einstein equation on the spherical symmetric solution plus perturbation. And okay, but that might be harder.
You mean like getting these coefficients from the analytical?
Exactly,
Not
actually computing, not assuming as an EFT coefficient. But in principle, you can just solve everything analytically. Take the spherical symmetrical solution, and that's not too difficult. Then perturb it and see the perturbation, how a quadrupolar, basically, you take a quadrupolar field, you didn't take electrodynamics with me, so basically, you take the standard solution, which is not standard because of course here you're outside the GR. And then you introduce a quadrupolar field, which is now would say, spherical harmonic basically introducing Q cosine square over R cube is a typical profile of a quadrupolar field, no? Because it's 1 over R cube, the monopole because it's 1 over R, the dipole 1 over square, the quadrupole 1 over R cube, and it must have a theta dependence. It can be independent because then this is basically the point, no? To spherical harmonic. So you add this perturbation, sorry. You know, the solution of the box equation for the spherical harmonic cube is either 1 over R cube or R squared. For the monopole is either 1 over R or R to the 0. For the dipole is 1 over R squared or linear. For the quadrupole is 1 over cube. So basically you turn on this field at infinity and you see what is the matching, what the matching condition gives you for this. And in GR is 0. And in non-GR, in general, it doesn't exist. So this is the way to compute the quadruple. And there are many papers in it. I mean, it's not a super original idea. There are papers in the literature that compute this quadruple field. The problem is that the fact is that this modification of GR are virtually infinite. Think of any. And the paper in the literature only cover a handful of them. As long as you don't have motivation for any specific modification, I mean, any computation is worth it. But okay, yeah, in September you go to London. Yes, so maybe this September it might be too tight. Let's see. Okay, who is younger? You again?
Yeah.
So you
Like exam first. So I am my name is Leon. Nice to meet you. I've started my PhD here at Ricardo and another professor at the University of São Paulo 2 months ago, and we are studying primordial black holes as a candidate for a fraction of dark matter. I'm currently studying its formation and evolution in the early universe, and how it will merge, and there are different ways signatures that will come from.
Yeah, but this wouldn't be the black hole of light, no? Explain better. These are not the light black holes. These are which kind of black holes?
More black
Yes. So what distinguishes them from the light black holes?
those are not astrophysical. They are very light, at the order of solar masses.
Well, possibly less, no? Anything will be asteroid to solar masses.
Yeah.
You know.
Yes.
And so basically their measured history can be very different from light black holes.
Of course, yes, we are looking for very small scales, meaning that it is on the region that light cannot see. So,
No, I want to help you, but I don't know what you want to say. What you want to say. If you tell me what you want to say, I might help you.
So you asked why it is not in the light?
No, I mean, keep the story. No, I mean, they don't want all the details. Just the story. I mean, come on. You're building a movie, no? In these 3-4 years, you're making a movie, but you're the script of the movie. You just have to build every single scene. The scenes are not printed yet, but the big picture is there.
Well, the big picture is there. We have the black holes forming the early universe, they will merge, and from the gravitational wave signatures, we will try to see how much the radiation will be released in this merger.
Yeah, I mean, there could be a hierarchy of mergers, no? It would be non-trivial to see. I mean, they appear, suppose they appear as some hierarchy. And when the universe was very cold, as hot as death. And then they appear there.
Mergers tend to be laminar.
Okay. Then they appear and they must find each other. That's already not trivial, no? They must find each other. So one has to solve now the revolution, the dynamics inside the primordial medium.
That's a part. Yes.
So, on one end, sending their mass low, it means that they can be measured. And so it might be easier to find. But then if the mass is too low, A, they evaporate, and B, they won't have enough attraction to overcome the expansion of the universe.
Okay.
So there must be a sweet spot. They cannot be too low, otherwise they won't find them. They cannot be too heavy, otherwise they are too sparse, and then again they won't find them. They won't find each other. So maybe there is a sweet spot of masses in which they are not too dilute and have them massive enough so that they can find each other. And what we want to investigate first, we have to investigate that, how they find each other, and then.
And the interesting part is that because black holes inside of me, they will get drag force on it, and this will precipitate into new density perturbations, even before the formation of the power spectrum of the same beam.
So no, basically we want to study the hierarchical relativity. So these being light and being many, once they merge, they shoot. Because
They shoot.
So they merge and they shoot. Not the first generation, but after the first generation they do not, because if you get one spinning and one non-spinning, the diagonal is shooting. You get some kick. And so this kick in the primordial medium can generate density wave that can trigger further formation and further encounter. So the idea is to see if in this method we can trigger several generations of binary mergers. Because basically one generation in the primordial medium won't have a interesting signal. But if there are 6, 7 generations.
But what's the range of masses of, like after 7 generations, are they still going to be primordial? Because I mean, their mass is going to increase.
Yeah, but linearly. So
Okay.
if they start with asteroid mass, it will be 10 times.
So you're not interested in like, because say if LIGO was to see, confidently think they saw a subsolar mass black hole, it would be primordial.
No, these are subsolar, I mean, we don't know, I mean, you have to find what is the sweet spot of the mass, then you haven't found it.
Okay, we're working on tensor masses.
Tensor masses, no,
Yeah.
that's just, that's an input, which is justified by the because we know the gravitational wave at this power rho plus peak. The light of black holes, no? Have this power rho plus peak, you don't see it. So say I don't know, not say I don't know if you don't know. Come on, we discuss this. Switch off. The distribution of light black holes, so it goes up to 16, it starts at 5-ish, and it's like this. This is a logarithmic scale, and at 30 there is a peak.
What's on the axis?
The mass. This is the differential distribution of the masses of the light black holes.
So the mass is on the x-axis.
So yes, it's just thanks. It's just the distribution of the mass. So. And this peak is not a statistical fluctuation, it's there. So apparently there is a surplus of black holes in this mass region. So there was a period in 2016, there wasn't yet a surplus, there was just one event there. And so Kamikoski said, oh, okay, this could be primordial black holes. So and he tuned the density fluctuation scale to produce black holes in this mass.
Full hierarchical measures.
No, just you have the inflation, standard inflation. Okay, in inflation you have the power to expect power, and in the 10 to minus 2 in megaparsec inverse, with the parcel inverse, we have CMB that constrains the power spectrum. But then if you go to the scale of much higher scale, like 10 to the 3, 10 to the 5, the parcel inverse, you have no information at all. So you might just invent that there is a peak. And if this peak reaches 1, this is 10 to the minus 5, this is CMB instead. If it reaches 1, then you will have the production, stochastic production of black holes at a mass set by this grid, the density of the universe times lambda cube, where lambda is the universe of this. And so, I mean, since this scale is completely adequate, you need to produce 30 solar masses black holes. That's what you need in this 2016 paper. Now, the funny thing is that in 2016, you couldn't know about PDA. So what happens, if you allow this surplus of density fluctuation at a scale, then here the density fluctuation is 1. But then you generate gravitational wave because this is the scalar density fluctuation, and this is like a transverse trace to the energy momentum tensor. So this will generate primordial, via second order scalar fluctuation, will generate primordial gravitational waves. And you know, if you tune the scale of the black hole generated by this fluctuation to be 30 solar masses, what is the frequency of this gravitational scale? The gravitational wave. That's some miraculous, no? That he published this in 2016, so it wasn't thinking of PDA, of course. But then in 2023, people realized that this mechanism produced a peak of LIGO black hole and the PDA excess. Okay. Maybe it's just a coincidence, but it's worth investigating.
What is this PDA excess?
Have you never heard about PDA? Okay, good that you asked that. So what happens is that, okay, let me give you the picture. So we are sitting here, so the center of the galaxy is here. So we are here at 20 kiloparsec from, no, we are 20,000 years, so we are 8 kiloparsec from the center. And we see pulsars all over our galaxy. Okay, we see thousands of pulsars. So the light of this pulsar is very regular, no? Because they are neutron star rotating. We see them one every round. We see them very regularly. But every now and then there is a little jitter on the time of arrival. You may think, okay, that pulsar is having a starquake, so it might have a little jitter or something. But then you do the following. Suppose there is a gravitational wave of a huge wavelet passing by. Then you will induce some jitter in the time of arrival that is correlated. Okay. They checked for it, and they checked, then they saw that there is some amplitude of gravitational wave in the range from 10 to the minus 9 Hertz, 10 to the minus 7 Hertz. That goes roughly like this, with a slope of minus 1-ish, very-ish, but slightly negative. Now the amplitude here, I don't remember, is 10 to the minus 15-ish in HC. Okay. It's small but not that small. And they say, okay, because through the correlation among the time of arrival of around 60 pulsars, they know that there is a gravitational wave that must have induced that correlation. So why this is the frequency range? Because basically you check of these irregularities in the correlation over the time scale of the observation. The observation for the youngest, for the pulsar that has been followed the least amount of time is 1 year-ish. Some pulsars have been followed for 10 years. How much is 1 year? That's a good number to remember for all of you. 1 year is 5 10 to the 7 seconds. So if you do the inverse of 1 year, that gives you 3 10 to the minus 8 Hertz. So that is the scale of nano. It's called nano. Nano is 10 to the minus 9, exactly for this. Okay. So of course, as you accumulate more data, then you move the low frequency beam a bit further. But you have to wait 1 more year to move by 1/2 in the grading scale. During our lifespan, it won't move much. So 10 to the minus 9 it is, as it is. And the upper frequency is by considering smaller chunks of of data. And basically, you lose sensitivity if you consider small chunks of data. So basically, if you consider chunk of data smaller than what would give you 10 to the minus 7 Hz, you basically lose sensitivity and you start getting noise. And so you don't see any here, the noise enter your traveling noise. Okay, so this is PTA, pulsar timing array, detecting an excess in the correlation of irregularity of pulsar arrival. And it's in this frequency band, 10 to the minus 9, 10 to the minus 8. And people say, okay.
So the vanilla explanation is that?
Yeah, it's not. The vanilla explanation is not this. It's not second order scalar equation. The vanilla explanation is that there are, so this is our galaxy, and some 10 billion, yeah, some redshift 10-ish or so. You have galaxy mergers. You have natural galaxy or the supermassive black hole at the center of the galaxy merger. So you can do the math. If you place this at redshift 10-ish, the distance they need to be has to be of the order of 10 to the minus 1 parsec. So just to give you the distance as the center is 8 kiloparsec. Okay, 8 kiloparsec as to our center, and this distance, so they have to be much closer than what. Basically, there must be not a mean spiral of a galaxy into another galaxy, but really a mean spiral of the center of the black hole into another black hole, because it must be very close to astrophysical on astronomical scale. So if they do this and you do the redshift from redshift angle, you get a signal in the PTA frequency band. And the nice thing is that, in principle, I mean, not as many as you can, but you can put quite many of them, and you imagine that there is some stochastic superposition of the signal, okay, that you are seeing. So this is the vanilla explanation of the PTA, but there is some tension. So Zattariaga published a paper in that you cannot explain the slope and to this mechanism. So people are waiting for more data to lower this noise. And once you lower the noise, then you understand if it goes like this, if it goes like this, if it goes like this.
Yeah, I think it's going to be a big drought in, I think, maybe half a year, because there's different collaborations. So there's like nanograph, which is the US, there's the Chinese ones, there's the European, so EPTA is for the European, and they're kind of all looking at different parts of the sky. So they're looking at different pulsars, and then some of the pulsars are common. And so when they publish the results, they kind of all publish the same results in sync using their pulsars. But now there's the whole pulsar timing array world collaboration has been trying to like combine the data from all the different collaborations so that they have more pulsars. And so they're gonna publish a paper in half a year or maybe a year where the sensitivity should be better because they'll have more pulsars.
Of course, all particle physicists got excited because they don't have particle data to analyze anymore. They say, oh, there must be a phase transition from the Higgs potential here to the modern universe. And so that's another sort of.
Some people also see like cosmic strings, no?
Yeah, but cosmic string, I will put it further high in the scale of exoticity. I mean, you know, cosmic strings were very popular in the 80s, I mean, 40 years ago, for explaining the seeds to form galaxies. The universe is very homogeneous, but if there is a string somewhere, then matter starts to cluster around and they form a galaxy around. And then it was killed by CMB, because CMB showed that the characteristic of the perturbation that didn't fit that, but did fit the outcome of inflation. And you studied the cosmology course. So, yeah, maybe you already did now, Roger. So this model of strings was killed, I mean, it was really buried in the 90s when it was starting to study physics, but it was already kind of dying in the end of the 80s. But it was the CMB in the 90s that killed this model. But still, you find it in many books. I think there are a lot of papers in string, they are revived every now and then, not for explaining the primordial perturbation, the primordial single galaxy, but for explaining other things. Okay, so this was the parenthesis about the PTA. So going back to primordial black holes, yes, you can assume that there is a spike in the primordial perturbation to produce primordial black holes. You can put this spike wherever you want, and so change the mass of the primordial black hole accordingly. And so if you put the spike at a higher K, then you make collapse a smaller portion of the universe, and so it's lower in the mass. So you can bring this mass to 10 minus 10 solar mass, 10 minus 15 solar mass, just by pushing this pipe. And here there's no constraint, so whatever. And okay, then you forget explaining PDA, quadratic perturbation theory, because if you move this pipe from the value that gives you this, then you don't get this figures, but who cares? And then most likely won't be the explanation of PDA. And so you can move now the premolar goes here. And so when you create this premolar group, you can create many of them, so they can encounter each other. And so if they encounter a lot, what we want to study is the hierarchy. I mean, how many generations they can give rise to, how many generations of nature. So why are we interested in that at the end? Because
what do you mean by that generation?
yeah, I mean, you do a merger, and then the remnant of the merger might encounter another remnant of another merger. So second generation, third generation. So in principle, you can go up to some, you can go to 100 generations, but 5 or 6 you can. And what you get with this is that you radiate, you basically convert rest mass to gravitational radiation up to, number of generation times 5%. Now, 5% is what you convert from mass to radiation in each merger. If you do it 10 times, then you are converting 50%. Okay, then it's not really very important. Okay. And this is interesting because that's what you need to explain the Hubble crisis. You need a late conversion of radiation, of matter to radiation. Okay, that's a bit far-fetched, and that we get there in 3 years. Yeah. So first we have to understand how the generation happened. So once we understand how the generation happened, then we see if we can account for an important transfer of energy from rest mass to radiation.
Is for that curve of number of detected binaries versus mass, is what you plot there in the middle?
Sorry, I completely lost.
That plot number versus n.
This is LIGO. This is
Yes.
LIGO of black holes.
And it's just the result observed. There is
Yes.
no physical explanation.
No, this is just observation. Of course, you don't observe many more smaller black holes and more massive. If you look just at the numbers, the distribution is like this. The problem is, the fact is that these black holes you can see to much farther distance because they are more massive. So you have to take into account the observational bias. That this you see until very short distance, and this you see until very large distance. If you take into account this, you transform the histogram of the observed massive black holes into the histogram of astrophysical black holes, which still points to more light black holes than more massive. You see what I mean? So it's a selection bias. Now we observe very few black holes of 5, 10 solar masses, very few. The bulk of the black holes is at 30 solar masses, 40 solar masses. But this means that the 1, 2, the 5, 10 solar massive black hole must be much larger in number because we can observe them only until basically 200 gigaparsec. Whereas the 30 solar massive black hole, we observe them until 2 gigaparsec. And so this must be much more numerous than the other because we see few of them, but we see only in the near universe.
And what about there's a mass gap, right?
No, the mass gap is pure astrophysical, it's not observation. So we observe black holes actually, we observe, Max just said, we observe a black hole with 4 solar masses. So observationally from LIGO there's no mass gap. Even here, so there are 2 mass gaps astrophysically. One is a 60 solar mass, and that's complicated because it's thought that very massive stars, 200, 300 solar masses, they live their life very, very quickly, and they have such a huge pressure at the core that they should explode by positron and electron liquidation to radiation. So the 200 solar massive stars that should give rise to 60 solar massive black holes should explode and do not give rise to black hole. So this black hole should not exist by astrophysical formation.
You can hire people.
Sorry?
You can have higher people, right?
You can
They can be formed for higher people.
For my rank, yes, by rank are very rare. You can estimate that basically they should amount to 0 in this case, basically, hierarchical mentioned.
It is not affected from 62?
Basically, there should be a gap from 60 to 100. So anyway, higher massive black holes, light doesn't see them because they're too massive. There should be a gap from 60 to 100, then what happens later, light doesn't care. But of course, ET might care. Okay. So ET will probe this intermediate massive black hole would be ultra interesting. But for LIGO, there should be, astrophysically, you expect this gap. In practice, we saw one event here, so it's not very clear if the mass gap is there or not. But you know, by then it says there. I wouldn't speculate too much on that.
When you say about ET, those are compact binaries as well?
Yes, ET Einstein telescope will look at lower frequencies, so we'll look at bigger black holes and black holes above 200 solar masses. But then there is the other mass gap between 5 and 1. Basically, there shouldn't be any black hole because a star that is not enough massive, that implodes, would have a shock wave. The matter that implodes will hit on other matter and should have a shock wave that sends everything to space, back to space, unless its mass is really high. So basically, black holes from 5 to 1 solar mass shouldn't be formed by astrophysical collapse. But we saw one black hole here. LIGO saw one black hole. So what do you say? Was a black hole that was a recycled black hole from my electrical measure? Was a primordial black hole? Maybe we shouldn't trust too much the astrophysical mechanism. You know, astrophysics is very rich, or the other way to put it is very dirty. And so there are a lot of things which are not under control. I shouldn't trust too much. But okay, there is an event here. It's worth being considered. There is an event here. They are at odds with the common law of astrophysics so far. We'll see.
Time will tell.
Yes, but I mean, these are the mass gap you hear about in literature. The low mass gap, the high mass. Okay. And they are completely different. They are completely different reasons. And LIGO is a slight tension with both of them, but you know, at the moment the tension is mild. Yes, and in 04, the masses are not public. You can go to the website and see all the events of 04, but not the masses. But still, if we saw a mass here or there, it might have been published already because it would be an exceptional event. By the way, you're not in live, right? Ah, you are not.
But you're.
I am. Yes. Okay, so now you want to say anything more about your project? I talked more than you. That's
Yes, there is the part where we explore the role of those kicks inside the
to do the hierarchical mention.
merge.
Yeah, because astrophysically the kicks are unwanted to do hierarchical mergers, no? Because if you think of late-time mergers and you do a kick, the kick can even send you out of the good region of the galaxy. Whereas in the primordial universe, where the redshift is very high, is 10 to the 4, 10 to the 5, a kick might create a sort of sound wave that might trigger further encounter. So that is completely different. The kick is welcome. It's not like in the late universe. So now we are studying the effect of the kick in triggering more mergers, rather than making the black hole escape.
So you want the kick to make more mergers?
Yes.
So you can convert more mass to
radiation, yes.
radiation.
Yeah, in the primordial that should work because matter is not ground, there is matter everywhere, so a kick actually creates a sort of pressure wave that makes the star collapse. In late time galaxies, no, a kick is unwanted because a kick sends you out of the globular cluster wherever you are, and basically you are lost, the black hole is lost. That's why it's a problem to create a hierarchical measure in late time universe, because you create the object, the final object, and that's basically, it's very, very unlikely that it hits on another thing. Whereas the universe before galaxy formation is another story that you will tell us next year. Next 6 months, maybe. 3 months.
Tomorrow.
Okay. great talk. I mean, I don't want to keep you guys, and if you want to leave any time.
Yeah, I can be brief. I started my I started my PhD this year with Professor Student. Right now, my main goal of my research is to develop a neural network algorithm that align with the Post-Newtonian approximate and the data from LIGO, Verb, and Kuiper can find mismatches between the eccentric waveform formalism, and with this mismatches we can hopefully
No, we haven't talked about eccentric waveform yet. No, come on.
No,
we are having this circular for the moment.
Yeah, no, to be brief, I am giving you a big picture what I am going to do. Yeah, and right now I am fixing the circular one. The goal is to develop this neural network algorithms to find this mismatches now to the circular orbit and later to the eccentric one, and understand how this mismatch will affect the detection of these binaries and how they will affect as well the parameterization, the estimation of the parameters of these binaries.
So mismatch between what?
The difference between like the template that I have from the
Which is TerraRF2, basically, no? TerraRF2.
Yeah, TerraRF2, and the data from the LIGO, Verb, and Kuiper detection. So I am developing an algorithm to find these mismatches, and I don't know which order of the TerraRF2, and find these mismatches and how they affect all the detection and all the parameter estimation of my binary.
Yeah, eventually you want to see if you can put constraint on modification of GR, no?
Yes.
But the problem is also we say that you have a huge degeneracy between a physical parameter and fundamental GR parameter.
Yes.
And the way neural network we have to disentangle the degeneracy, to me, is a black box. But
I think too, but I am working on it. This is the exciting point. One of them.
yeah, and this is done with Luis. So Luis is the starter.
But I think I'm confused still about what you're doing.
Ask him, he knows.
So you're computing, so you're looking at the events from say O3.
No, right now I construct all the formalism of TerraRF2, and now I am building a catalog of all this data from the same intersections of LIGO, Verb, and Kuiper, and construct the analytical, such as waveforms. And when I have both of them, I am developing an algorithm of neural network to find this mismatch between the theoretical and the detection part.
So you're in the spiral phase.
Yes. Yes, you can progress you can construct all the waveform, but now I am focused first in the spiral phase because it's easier. But now the hard part is to develop this neural network. I work a few years now with neural network, but it still is hard to work with a great amount of data that can help us to find this difference between data and templates.
And why TerraRF2 over another model on it?
I mean, because it's analytic and it's easy to see. It's a light of under the lamp.
So by mismatch, it should mean basically integral we involve the noise PST of the detector, then the signal and the actual template. That's what we mean then nonlinear.
Yes.
That's literally.
Yeah, and into different orders of the templates. So the second, the third, so the Post-Newtonian approximation. And yes, the main goal is to develop an algorithm that will find to each of the Post-Newtonian orders this mismatches, and gratefully when
these mismatches occur, which order.
But by find, you mean, it's just an integral, right? So you just do an integral, what do you need?
Yes. Luckily, the neural network will give me this difference. So I am, as the student said, this is a great black box. But
I guess the PN coefficients are going to be some of the free parameters, which will tell you how GR are going to be modified.
Well, that's not clear to me, but the point is another thing that's not clear to me is what is the, say, the statistics that we use. I mean, is the mesh filtering product that will tell you how a waveform is close by, or the neural network will have their own metric to evaluate the difference among waveforms?
This is the hard part I talked to you last time. Yeah, I have to figure it out.
Yes, without knowing anything, I would try the mesh filtering standard
Yes.
formula. But
Yes,
maybe,
this is the first step.
maybe there are other quantitative indicators. No, sorry, about your question. So, basically, yes, you have a functional form that is given by Pn, but the coefficient of the Pn expansion, of course, depends on the astrophysical parameters that are whatever they are. And so they must be let vary, no? The Pn coefficients.
Yes, they do vary.
Because they also depend on the field of gravity.
Yes, but basically, the start of the project is to use the Pn formula face value with the variable coefficients. That already should constrain. I mean, it's not the most generic parameterization you can have. No? If you get F2 but with variable coefficient because of the mass and spin, that's already not a generic function. It is somehow.
Yeah, the main goal is that the neural network will find these three parameters and find how they best correlate between each other and find these mismatches between these three parameters.
But isn't this what basically MCMC does, just with a different method? Like MCMC is like basically, finding the minimum of a mismatch.
Yeah, but here you have to do for population, no? Because for the single event you don't want to produce the events, the coefficient for a single event, no? You want to see the deviation of a population from an underlying population, no? It's a kind of it's a meta MCMC. It's an MCM of MCMCs, which you cannot do with MCMC as far as I know.
It's too expensive.
But each event in your population, each event in your population will have different coefficients that this requirement that So how can you go to the population? Like I understand this point, it's just you're trying to fit and find the best parameters for each data.
Yeah, the hope is to see this globally because I have all the data analysis from Ricardo and find this is the hard part because I am starting now to develop this neural network that will find, and I don't know how this is the trick part of this kind of method because it's really a black box. So I don't know if how much free parameters I can give to the code or how they will see the template in relation to the data there's already there. So I'm trying to figure out how to start from the base, from the basic, and then find how the model will, I don't know what to say this, will rearrange between the data and templates. So right now, I know it sounds a little confusing because working with neural networks is a little confusing. But right now I'm just preparing my template and preparing my data to start to feed the neural network. So right now I'm in the big steps of neural network. Then I will be able to see these parameters, to see this little, I guess parameters to the correlation between them. So yes, see the perspective of population data.
So your training data will be just injected data to.
Yeah, for each of the parameters and.
Okay.
Yes, it's very cost, meaning computationally, but this is the real job, to find this mismatch between the data and what we find in templates.
Yeah, but today, if you don't do AI, you're out. I mean, you have to do AI or something. I know, I'm also very suspicious, but since everybody, there must be something in it, otherwise. So I want to understand a little bit how it can possibly work. I mean, it does work to some extent, but I don't understand how it can possibly work. But to some extent, it does. It does.
I mean, it's probably going to be used for parameter estimation, like also next observing machine.
That's been used already.
Yeah, it's been used already, reviewed, and it might
Yeah, it's not reliable.
but it will in like as well.
Oh, but I mean, production samples, they're not produced with the AI. No?
Not yet, but I think it will in the future.
Yeah.
So that is Steve Green's.
I think hard, yeah.
You also do in Boston. I mean, people in Boston do.
People, yeah, heavily.
Okay. So, yeah, if you don't want to get an expert from history, you have to jump on AI. No, I have Strominger is this big snake theory guy. Until a few years ago, he never did computation with the only pen and paper. Then at some point he started to use mathematics.
Yes. But I agree, it's a bit of a black box.
Anything more today?
Yeah, but it's a fun way to think about it. I work with some companies with neural network, and this is the hard part, because some client will tell, oh, what are you doing with our data? How this is going to, I don't know. Just neural network, just find a way, and we have to use this and try to find a sense. But deeply, neural network, we don't know how they operate, how they work. We know the structure, we know how to proceed, but how they find this way and how they come up with new parameters, new estimation, new forecasts, it's totally
Have you read about INCO?
I'm sorry?
Have you read about INCO, the machine learning curve for gravitational wave?
Yeah, it's one of my reading lists, but I
Yeah, maybe it's useful.
Yeah.
What you're doing. Yeah.
yes, sure.
Because they've been doing this for a couple of years, so I'm just having a look at what kind of instrument structure they use.
Yeah, probably the structure, I don't know if they will form, I don't know. But anyways, the black box part is the trick one, is the real where the real magic happens. So it's really unique for each formalism.
Ricardo is a history professor, so you want to say 2 minutes or
30 seconds. I'm working with the problem in self-force computations, specifically taking care of the analyzing the separatrix. When there's a separatrix inside this region, the parameters, the impact parameter, and energy, you have a meeting between two of them, they merge, right? So all this is corrected by self-force computations.
Okay. So tomorrow, the last lecture was correctness.
What time?
It's
Same time?
just
It was at 4 last night.
no, tomorrow will be at 2:15 like today.
Okay.
And then on Thursday we move at 4 because you used to have a class, but your class is over.
No, I will have class tomorrow.
Now on Thursday you want to have class at what time?
Yeah, 2 to 4.
At 2 to 4?
Yeah, quantum mechanics.
Okay, then why did they set your class for tomorrow at 2?
I don't know.
No. No, let's meet at 4 then. Let me check the lecture time. Okay. So the official website says. No, tomorrow at 4, sorry, it was right. Tomorrow at 4 and Thursday at 4 to comply with.
Oh, both at 4.
Yes, tomorrow at 4. So, wait, tomorrow I have to leave at 5:30 to pick my daughter